Hello team, welcome to a video guide for Compiler's Assignment 4, Code Generation. In fact, we're going to be focusing on unoptimized, simple, correct code generation for now, leaving common optimizations for later. In this video guide, I'm going to skip deserializing the type checker annotated AST, assuming you know how to do that from previous assignments, and instead focus on generating cool assembly for object, int, IO, and main, in particular for a program that's something like new main.main, which then calls out int on some integers. This will involve thinking about virtual function tables and laying them out in an assembly program, thinking about the calling convention so that we can call main.main and also call io.outint, thinking about object layout and constructors. We'll want main to have some fields, and also the integer class has sort of a hidden implicit field, the contents. We'll need to reason about all of those. And we'll do a lot of this through stack machine code generation, just as we covered in class. In particular, covering the new dynamic dispatch, int plus variable read, and internal cool expressions. And as we do this, as we're generating code, we'll need a convention for how we're using the registers, say as various temporaries, and we'll have register 0 be the self pointer and register 1 be the accumulator, and we'll use registers 2 and 3 for temporaries if we need them. All right. An important thing to note about this video guide is that it will have a bit of a, shall we say, let's play format. I will be doing my best to construct this code generator in real time without multiple takes. This does mean that you may have to struggle along with me as I make some obvious mistakes or bugs, perhaps that you'll be able to see on the screen before I will. The advantage of this is that, especially if you're struggling with the assignment, it should give you a feeling that it's possible to sort of sit down and do it, and that everyone makes mistakes, but that it's possible to debug through them. All right, so let's get started. We have a simple, cool program. Class main inherits IO. It has two fields, A, which is an integer that's going to hold 222, and B, which is an integer that's going to hold 333. And then we have a main method that calls self-outint on AAA. And when we run this, we expect to get 555. And in fact, we do. We can also ask cool to produce cool assembly for it. All right. And see all of that produced. Suppose we want to make some sort of code generating program that's going to print out much of the same stuff. I start all of my OCaml programs the same way. Wesley Weimer, CA4, simple code generator. And we're just going to think about some of the things that we mentioned earlier, right? Object, int, IO, main, virtual function tables. I'll want to get started by laying out some types. For example, the types that I would read in for PA4 to correspond to cool expressions. I am not going to I am not handling locations. That is left as an exercise for the reader. But a cool expression could be an integer literal, and note that we use in32.t because the cool oxem requires it loosely, or because OCaml's default int is going to be 31 bits or 63 bits or something like that. We can also have a plus of expression times expression. We can have new of a type. We can have dispatch of the receiver object, the function name, and then the arguments. We can have an internal expression, like internal IO out int. We won't do strings in this example. We'll just do ints, which will be quite enough fun. Are there other cool expressions? New dynamic dispatch, int plus variable. Oh, of course, variable. And you could have a reference to a variable like x that's somehow in scope. And I'm going to use these expressions to denote method bodies and also attribute initializers. So another to-do, we are skipping deserialization. In order to make this go faster, I don't want to spend time reading in all of the possible types of cool expressions. So instead, we will just declare global variables as if we had read in the annotated abstract syntax tree. So for example, at some point, my main A initializer expression is just something like the L in OCaml, by the way, here means 32-bit integer. Main's B initializer is just 333, and main is currently dispatch expression, right? Where first there's a reference to a variable self, and then we're calling the outInt procedure on it, and then we have a list of arguments. There's only one argument, it's plus of variable A and variable B. We close off the plus, close off this. All right, so it wraps a bit, but I'm going to write these out as global variables, but you can imagine that we could have obtained them by deserializing the CL type file. All right. Similarly, I'm going to want some sort of parent map. All right. And this we could totally read in from the annotated abstract syntax tree, but I'll just set it as a global variable. We will add to the parent map that the parent of main is IO, that the parent of IO is object, that the parent of int is object, and indeed, we'll have a get parent of some class C. So some things like main, IO, and int have parents, and potentially everything else has object as a default parent. So indeed, I don't even necessarily need to write these. Main inherits from IO, and that's pretty much it. You'll note, this is a fix me, we are only handling main, IO, int, and object. You'll want to add string and bool and potentially other classes as time goes by. We have main inheriting from IO. All right. One of the other bits of information we would get from the annotated abstract syntax tree, from the hard work that people did in the type checker, something like the class map and the implementation map. All right, so up here we have the parent map, and the class map maps class names to their fields and initializers, their corresponding fields and initializers, and potentially even their types. So it seems, we'll have to come back to this decision later, that the only really important entry in the class map for us is going to be something corresponding to main. We'll just leave a little note to ourselves. We may want to handle the contents of an int here somehow. We're going to have to figure out or come up with a, what's the word that I'm looking for? A unified strategy, a policy, a rule, a calling convention almost, for getting out the hidden contents field, the unboxed integer that lives inside a boxed integer. All right, so the type of our class map, we'll do something cheap like having a hash table. All right. It's going to map from strings, right, like main, to lists of attribute name, type name, and expression pairs. This is a string, and an expression. All right. So there's our class map, and in particular, there is one class map. Fix me, read in from the CL type file, but we're just going to hack it up. By the way, this let underscore, this is a common OCaml convention way of having a sort of global initializers. All right. But we're going to add to our class map that class main has a, which is an int, and its initializer is just 222. And we have b, which is an int, and its initializer is 333. Right. And we may at some point want to add that there's a contents field for int in a bit. Right. We also have our implementation map, which conceptually maps a class and function name to a list of formal parameters and their types, but we won't need that, and the method body. So once again, we're going to use a hash table to represent a mapping because we're super cheap, right? We want to get something functional and correct as quickly as possible. And then here, our list of formals will be just a string list. This is the formals, and the method body will be a cool expression. Right. Now this is sort of a default way of thinking about the implementation map. This is a sort of an inlined version, if you like, but we may actually want something a little different. Right? We want to map class and function names to a list of formal parameters. That's good, but maybe not so much to the method body as instead the sort of name of the original class providing the implementation for that method body. And what do I mean by that? Well, it is possible in cool to override behavior. So we would want to know that if you're calling class A's f method, that you get this body, A gets A plus D. But if you're calling B's f method, they override it and we get B's version of f. So, so potentially instead of a string list times an expression, we'll have a string list times a string. And we will, oh my gosh, going to add to our particular implementation map. Fix me, read in from the CL type file. Well, it turns out that if you are calling main, there are no parameters, and the version of this we want you to emit code for, right, is main.main. And just to sort of demonstrate how this would go, suppose there were some class foo that would inherit from main, right? Then we would also add that foo.main gets main. But if there's some class bar that would inherit from main and override main, right, then bar main would be bar.main. Okay. Where do we get all of this? From the CL type file. File is fairly dry, but for now, we don't have any of those. We'll just have class main. There's mostly going to be this one method. But we'll just make a note for ourselves, fix me. We may want new to be an implicit first method for all classes. Right? How would that potentially look? Something like main.new would be some new main constructor, something like that. We'll take a look at how the reference compiler produces some of those in a bit. All right, let's see. Enough nothing happens. Currently, our code generator doesn't actually do anything. But let's see if we've been able to write this much OCaml without making some sort of type error. Fatal error. Yay, all right. You can totally ignore that part. I have multiple versions of OCaml on my machine just in case I need to compile different binaries, and there was a little mismatch between them. All right, so we have written OCaml code that did not immediately die. Ho ho, moral victory. So now, I'm just going to pull up what happens in the reference compiler produced cool assembly and indicate to ourselves that we want to do the same thing. So one of the things we will want to do is lay out virtual function tables. Right. And then another thing we may want to do is lay out constructors. Right. And then potentially, keep going down, object new, string new, right, object abort, object type name, IO. Oh yeah, we will definitely want to do at least one of these. We'll want to lay out methods, things like IO outint or main.main. Blah, blah, blah. We're not going to be doing strings, so we don't have to worry about string constants. We're not going to be doing equality handling. All right. I'm actually not going to spend a whole lot of time on that because students often just copy it out of the reference compiler, which I don't necessarily recommend, but is an option available to you. So less than blah, blah, blah. And then we also want to lay out start, which conceptually is doing new main.main. That's how you begin a cool program. Right? Those are all the things that, that we want to do. And right, just for simplicity, since we're not reading in from the input, we can just always write to some file like out.clasm. So let our output handler. So I'll just make a note for each one of these. Virtual function tables. Constructors. Methods. And start. And just to make these visually obvious, we'll have big line breaks, and then we can close out, F out, and declare moral victory. All right. Can we still run it? Did we produce our output CLASM file? Well, there's nothing in it, but it's potentially at least well formed. This should probably complain that there's no start. Label start not found. Excellent. All right, so now all we have to do is actually produce assembly to go into it. Tables. I appear to be spelling tables like it's some sort of science fiction race. But since it's in the comment, it doesn't matter, but we're going to watch me fix it in real time anyway. All right, so to lay out the virtual function tables, right, we can take a look back at the slides that go over this. Right, and we talk about how this is for object layout, vtable, headers, dynamic dispatch table. Right? That as we add methods, right, we just end up adding those additional methods onto the end of what we already had, so that there's always a common prefix. If color point inherits from point, then color point's vtable for the first few entries looks just like point, and then after that you can add the new stuff. Right? And we can potentially see that here if we compare the virtual function table for main against the virtual function table for IO. Right. Here we have some boilerplate stuff at the beginning. This is the name of the type in io.new, but then we've got object, abort, copy, type name, io. And we see that main has the same things in the same order, object, abort, copy, type name, right. Except that it has its own slightly different constructor. And then it has main.main at the end, where io does not. All right, so to start enumerating these, one of the things I will need that I could get implicitly from the int map or the parent map, fix me, obtain a list of classes in the program. All right, so for us, that will be object, int, io, and main. All right. And what I might do is iterate over each of the classes. And this strange double period convention, you might be wondering, where does this come from, or why does the reference compiler do that? That's so that we don't have a label collision if a cool programmer happens to have a method named vtable. You'd think, why would you ever do that? I'm sure we have a test that does that. Right. So this is our class name vtable. Right. And we are not going to bother with this string. This is used for type name, which I'm not going to implement in this simple code generation example. But we probably do want a constructor. Right. This double tab convention is mostly just for readability. All right. So we will have this.new, and then we need to figure out what all of the methods are. And most of our classes won't actually have methods, aside perhaps from io and main. So over here we're adding to these. Right? If you call main io, you get if you call main outint, you end up getting io.outint. And if you call io.outint, you get io.outint because it's inherited. Right. So potentially what I'm going to do is iterate through our implementation map. Right. And if there's anything matching this class, print it out. Let's see how that goes the first time, because this may encourage us to do a bit of a data structure change. Hashtable.iter, and we have a potential class C prime when we're iterating through this. Right. Here's our class C prime, and here's the method name. And if we find it, we will see the arguments as well as the, let's call it the particular method implementation used. Iterate over our implementation map. If C is equal to C prime, then I can print out that when you call me on this method name, this is me, this is the method name, you really want to visit the method implementation used. All right, see if we can run this through OCaml. How many type errors do we have? Line 82. List iter through all of the classes. Print out C, hash table iter C. Darn, we'll have to read the error messages. This expression has type string list, but an expression was expected of type string list. Yep. These four strings, the reason it says string is that I used commas instead of Python. That's why they pay me the big bucks. Commas instead of semicolons, because I was thinking of Python. Python in my heart. All right. Well, that one actually worked. So now let's take a look at the output. All right. So we've got object.new. Why are we? This isn't exactly what I want. All right. Because I have this line of code duplicated for no obvious reason. Let's rerun this and take a look at what's produced. So objects vtable, the first function pointer goes to object new. Ints vtable, the first one goes to int new. IO's vtable, the first one goes to IO new. The second one goes to IO outint. And then down here for main, we've got main new, main, and we should be calling IO outint. So the first thing we notice is that this second word I'm printing out is totally extraneous. The second thing we notice is that we're not matching the order. Remember, as main inherits from IO, it's supposed to have all of the functions in the same order. The constructor first, and then outint. But we've got outint coming last. You might think, well, like, why is that? And essentially, the reason is that we're using a hash table for our implementation map, and the ordering is not necessarily defined. So, suppose we want to represent this a different way. Suppose instead we say, oh, I want IO to map to the list. Outint takes no arguments and is implemented by IO outint. Main is going to map to the list. Outint takes no arguments and is implemented. And then also, main's main method takes no arguments and is implemented by main.main. So if I just rewrite my implementation map a bit when I'm converting it from the CL type file, I can make sure that I preserve the order. Right? I need these to be in the same order when they're inherited. And this is a problem you solved in CA4. Right? So we've already done it before. So now the type of my implementation map isn't quite the same. I actually don't need this type declaration, but for good OCaml brownie points, we'll include it. It maps to a string list string sort of maneuver. All right. And now what I want to do is, so my methods are try hash table find in the implementation map C with not found goes to nothing in. We're going to iterate over my methods. Here's the method name, the arguments, and the method implementation used. And we just want to print out the method implementation used. Does this compile? 79. Closing parentheses might be expected. We iterate over those three things. Main B. Help me out again. Line 79, 58 to 60. Here's line 79, 58. I've forgotten the word fun. All right. So now let's see if these print out in the right order. We've got the constructor first every time, and then we have outint. We inherit outint, and then we've got main. All right, this seems pretty promising. And we can actually compare it to hello CL_asm. Now, we're not doing this, and we're not including abort or copy or type name, but we've got the constructor first, and then outint, and then main. So we're sort of a subset of what the reference compiler is doing. So we feel pretty good about that. All right. Can we actually run the result here? Absolutely not. We still haven't provided label start. And even if we were to provide label start, we have reference to all these constants that we've never actually filled in. But we're pretty close. This is actually all we needed to do to fill out the virtual function tables. We're more or less done with that. And now it's as if we're making promises that we have to fill in. So we've promised to provide this object.new or int.new or io.new. And now we just need to do each one. So once again, I'm going to iterate over every class and start with a label. What do we call these? New. All right, for my class C. All right, so now I have potential room for every constructor, but I don't actually have any code in them. Now what actually goes on in the constructor, loosely, is that we need to allocate new space for the new object. This is like step one. Then we need to set up the fields in the new object. 2a is set up the vtable pointer in the new object. 2b is set each field attribute to hold a default value. And then 2c is execute all initializers in this new context. And then we need to return the new object. This is our basic plan for implementing constructors. Let's go see if we can see that actually play out in the version from the reference compiler. Hello, main, new, yeah, here we go. So there's some calling convention stuff about the frame pointer and the stack pointer, but here's the part where we are allocating space for the class using this alloc instruction. Right? So this corresponds to step one, right? This line. And then they store the class tag, the object size, and the vtable pointer. Well, for us, that's just the vtable pointer. And then, right, so here we are loading main's vtable and storing it. And then we initialize all of the attributes. So first we call new int to get the default value. Right, so here we are calling new int. This is 2b. All right. Here we're doing another new int. This is still 2b. And then there's an initializer. All right. That's 2c. And when we are eventually done with all of those, we return, and there's some calling convention stuff. We pop the return address off the stack. All right, so one of the things we're going to have to do when we emit constructors is actually get the calling convention right. And this is potentially tricky because you might choose to use a different calling convention for constructors than you do for the rest of the world for optimization purposes. We're totally not going to do that, I hope. But we have this slide function call and function definition bits here just for point of comparison. All right, so one of the first things we want to do, let's just say for now, like printf out, fix me calling convention stuff. All right. We're going to have to do it at some point, but let's sort of skip it for now. One of the things we want to do, though, is, where was alloc? Is allocate space, right? Have R0, which is going to be our self pointer, become a new object. Right. And actually, just to make that a little easier, we'll have self be the accumulator, or self be R0, and the accumulator be R1. Potentially, just in case we decide to change them later. Right. But this does mean that we need to know the size of every object. Right? So as we're thinking about constructors, right, the size of an object, well, for us, we have the vtable pointer, right, plus attribute 1, attribute 2, right, like field 1, field 2. Let's make it explicit. So the size is n plus 1, where n is the number of fields. But fix me, you might want a type tag, which you might need for case. You might want an object size, which you need for clone. You might want a bunch of other things here. So your size calculation might be different. From the class map, we can figure out the size. So let's see about figuring that out right now. So we're going to find these, right? And if there's nothing present, then you didn't have any fields. And we're going to take the length of that, and we are going to add 1. Right. Now, eventually for you, it'll be like add 3, but for now it's add 1. Right. So if we are mimicking the reference compiler, we can start emitting our first actual, real, in some sense, cool assembly instructions. And we'll load immediate into self the size. So yeah, we called that self, and this is the size. And then we can do alloc self self. All right, let's see how that goes. Oh, looks like we forgot a new line. Let's try that one more time. Oh my gosh, I can type. All right, so for object new, we think it's size 1, just the vtable. For int new, we think it's size 1. That's not going to work. We actually need more space for int because it has to hold the actual unboxed raw integer value. For IO, it's 1, and then for main, it's 3, and that's correct. Why is it 3? Well, we need space for this field A and space for this field B. All right, so hypothetically, our class int has some contents field, which is a unboxed int, right? That conceptually starts off at integer 0. Right. Note, unboxed int is not a cool type. It is a special sentinel value I am using to communicate to myself that I want to store the unboxed raw integer value there. All right. So let's see if that compiles. So now we should see that the size for int is 2. We can even tab that stuff over if we want. All right, so we have allocated space for the new object. All right? And now we're going to set up the fields. And indeed, let's pull out the fields here. For step 2 to set up the fields, and just iterate over all of them. Well, what do they look like? We have the name, the type, and the initializer. It's the field name, the field type, and the field initializer. All right. Set up the fields in the new object. Well, we can do all of that. Let's do the vtable pointer first. I will keep with what I had promised. Main, new. So at this point, this alloc instruction, it's like a system call, right? Allocates new memory of that size and has R0 be a pointer to it. So we want to store the class tag object size and vtable pointer. Well, for us, it's just the vtable pointer. All right, so conceptually, this is the code we want to be doing. Store the vtable pointer. Except that for us, this will be in location 0. All right. So we're going to load the address where we need some temporary register. Right. Which we'll also call temp1 because there might be a temp2 later. We're going to load into some temporary register our name.vtable. So this is our temporary register, and this is our class name. And then we're going to store into self bracket 0 the temporary register. This is self, this is the temporary register. Okay. Let's do nothing for now and just see if this prints out. All right. So here in our object constructor, we're loading the object vtable and storing it in the 0th slot in a new object. That seems right to me. Yep, all of this is looking pretty good. All right, so now it's time to do the fields. All right. And as we iterate over these, we'll need to keep track of where we are. I could do this with a for loop, right? So index 0 is the vtable. Index 1 is the first field. So if we have to store anything anywhere, we're going to store it at index. And then when we get to the end, we'll increment index. Right. So for many of these, if they hold an integer, we end up just calling int new, which in theory is going to put its result in R1. Right. And then we store that in the given index. Right. Now, all of this stuff about pushing the frame pointer and pushing R0, this is the same calling convention stuff that we haven't done yet. Right. But fix me calling convention stuff. We'll also leave another little comment. This is the this is the blah field of S gets a default blah. So this is the field name field of C gets a default F type. We'd want calling convention stuff, but conceptually, this is the code we want to be emitting. So let's just do it. We will tab over. We will load into our temp register this type.new. So this is our temp register, and this is the field type. And then we will call indirectly through our temp register. And then we will store that the self bracket index gets the accumulator. That was not, anyway. The tabbing in my comments, I blame the text editor. I don't blame the text editor. It's user error. All right, so let's see if that compiles. All right, so now we can see that for something like object, which has no fields, we don't do anything. But for something like main, right, first we do the A field of main, which gets a default int, and then we do the B field of main. And so this was the vtable, and this is the A field, and this is the B field. And indeed, you can make your life a lot easier by having extra comments. this is class names field name. So we can see that this is main's B field is at position 2, right? And main's A field is at position 1. That seems pretty good. But if you look over here, there's this unboxed int.new. Well, unboxed int is not a class, so we can't do anything like that. But indeed, the point of unboxed int is that it's not a class, it's a raw value. So what I'm going to do here is have a little check. We're going to match the field type with. And if it is unboxed int, I'm going to do something special. And if it's anything else, we're going to do this usual thing. All right. Begin, match field type with, and I have the begin and end because I want to make sure we always increment the index, not just incrementing the index in this last branch. So if it is an unboxed integer, someone is calling new int, then the default value for a new integer in cool is just 0. So I can load an immediate value. I'm just searching around to see how that works. Load an immediate value into temp and just get what it is, right? Somehow figure out what it is. And then I can do the same sort of temp, put this in the accumulator, yeah. And then I can store in self.index the value of the accumulator. So this is self.index and the value of the accumulator. So now all I need to know is what this int is supposed to be, but it's 0 by default. That's the plan. (142) has type string, but they're right. All right. So now object, still doing nothing exciting. Int.new. Here you see us loading the immediate value 0 and then storing it in slot 1. Right? And this is the special contents field that we have to reason about as part of our code generator implementation, but is actually and it's not really exposed in cool, like the user doesn't see it. All right, this is looking pretty good. So we have set up the vtable pointer. We've set up each field or attribute to hold a default value. Next, we would execute all the initializers in this context. So once again, we would loop over all of the fields. And depending on what they are, like if it's in, or in particular, on what the initializer expression is. Right? So if it's in unboxed int, then we don't do anything. There's no initializer to do there. We've already done it. But if it is something else, and it's some cool initializing expression e, then we would want to call or execute that code right now. And this requires us to have some way of generating stack machine code. Recursively generate stack machine code for a cool expression. We are definitely going to come back to this later because this is going to be much harder than I'm making it out to be. But loosely, you would match e with, and then for each one of these, integer plus new, something like that. There'd be a particular thing you'd be doing. For now, let us just leave a little comment, right? Fix me, generate code for cool expression. Okay. And recall, generate code for E, putting the result in the accumulator register without smashing anything already on the stack. All right, so we should leave the stack the way we found it. Leave the stack the way we found it. And for now, we're just not doing that, but we're going to get back to it later. All right. So conceptually, we would call cgen. This places the result value in ACK. And now we want to do the same sort of store. Initialized. Does this compile? Nope. And it looks like I've once again forgotten new lines. Where am I forgetting the new lines? Generate code for cool expression. Here, I forgot the new line. All right. So now for int new, nothing changes, which is good because we're just storing this raw 0. But for main new, we'd have to generate code for A's initializer and then generate code for B's initializer. All right. And we will come back and worry about that later. All right. So we've executed all the initializers in a new context, which is going to be tricky. And now we just want to return the new object. So potentially, as we're getting ready to leave, we just move such that the accumulator, return the new object, the accumulator gets the self object, and then we have more calling convention stuff. But then eventually we'd call return, execute the return instruction. All right, and let's go see how that compares to main new. So we've done all of this, and here we have the move R1 gets R0, and here we have the return. So we're almost there aside from this calling convention stuff, which we'll have to get back to in a bit. All right. After we've laid out the code for all of the initializers, and conceptually it's time to lay out code for all of the methods. And we get all of the methods from our implementation map. Something like this. The implementation map tells us my previous answer was a bit glib, tells us the order in which to lay them out for the vtable. We might say we actually get all of the methods from something like the annotated abstract syntax tree. All right. So we have two methods that we really care about. io.outInt and main. So, right. io.outInt just calls internal io.outInt, which is going to be harder than it sounds. And for us, main calls, well, we had this here. We already wrote that earlier. Right, so fix me, obtain all of the methods from the CL type file, right? You just deserialize it. I'm just too cheap to do that. So we've got all our methods. So we've got the method name, and we'll call it the method body. And we print out the method name with a colon. And then, as is so often the case in these tales, we have you know, calling convention stuff. We generate code for the method body, and then we would return. And this looks fairly simple. It's really just a for loop or an iteration. The heart of this is really going to go into this cgen approach. Let's see if this compiles. So for all of our methods, oh, I shouldn't have tabbed over the, cool won't care, but this will be a little more readable. So our two methods are io.outInt and main.main, which is good because they're referenced up in our vtables. But we're mostly not doing anything with them and then immediately returning. And then for start, right, you know, we can either have this as a third part, or if you like, we'll do just a little trick here, right? There's another method called start, and its body is, just write it up here, the start body is dispatch on new main dot main of no arguments. Right. This is hard-coded into cool. The CRM tells you to start cool this way. This is how cool works. Okay. So if we add that in, right, now we see start down there right at the end, and indeed, right, now we can just say includes the special start method. Okay. So now there are really just two big decisions or bits we have to code up remaining. One is the calling convention. Every fifth line we've said, oh my gosh, calling convention. We haven't done it yet. But the other is code generation for expressions. And actually, let's do code generation for expressions first. It's going to turn out that when we're generating code for expressions, we will want some sort of symbol table or environment, right, that's going to tell us where variables live. Right? And conceptually, when you're generating code, there are a few choices. It could live directly in a register, like self lives in R0, or it could be at some offset. Right? For example, it could be at something like frame pointer, bracket 4 or whatnot. Right? So this is a register and then an integer. Our symbol table here this type name is longer than I normally do. Right? We need to keep track of where everything will live at runtime. We know where it will live at compile time. That is, we know its location statically, but we don't know its actual value until runtime dynamically. Right? Compare environment versus store. So let's say that when we're generating code, we're going to have a symbol table. And I'm going to do, for now, very simple, very inefficient stack machine code generation. But this sort of, symbol table or environment, you'll want this when you do the numtemps optimization or the register allocation optimization. All right. So, what could E be? Well, one potentially easy choice is that we're asked to generate code for some variable x. If that's the case, then I can just, well, it's a special case. I can just match in the symbol table where x lives. If it lives in a register, or if it's at a register offset by an index. If it lives in a register directly, I can just move, the accumulator gets that register. Conversely, if it's stored at an offset, I can just use the load instruction instead. Line these up so they look nice. Didn't work. They didn't look nice. Oh my gosh. All right. Now it won't look nice when we print them out. Anyway, but that's the plan for looking up variables. All right. That seemed pretty good. Suppose someone wants to make a new integer. Well, conceptually, what I want to do is call, right? I can generate code for new int. Right? And now that this puts the result in the accumulator. And now I'm going to store. Right. Right. This is something we can do as the compiler. Directly access the secret contents field. I happen to know, where was it? We happen to know that the secret contents field for us is at offset 1. So into the accumulator at the contents field index, we will going to need an LD here because this is a 32-bit integer. We just print that out. All right. Note that this is, we know this is inefficient, right? We are making an entirely new int, filling it in with 0, and then overfilling it with I later. This is not fast. You could do something better, hypothetically, for an optimizer. All right. So, suppose it's time to do E1 plus E2. We are going to do standard stack machine code generation. We do cgen for E1. We push the accumulator. We do cgen for E2. So this is now in the accumulator. We pop into temp. All right. But now, when we did standard code for these before, they were just raw integers. But now I'm going to need to extract their raw integer contents. So we're going to load from magic contents, and we're going to load from magic contents, and then we actually get to add. Right. And now we want to make a new int, and then we potentially we'll want to like push temp just in case or whatnot. Make a new int, and then we are going to store into the accumulators field the raw integer value in temp. All right? So potentially maybe to make these clear, at around this point, these become raw unboxed values. We use unboxed. Right? Unboxed. So to actually do addition, we have to interleave operations on boxed and unboxed values. All right, but we can do it. So we call ourselves recursively and generate code for E1 using the same symbol table. That's mostly going to be set by the person who calls us. All right. And then we are going to push the accumulator. And then we're going to generate code for E1. Oh, we could say accumulator, but we've been so nice so far. And then we're going to pop into temp. And now we're going to load. Accumulator gets accumulator at 1. And this is the contents field index. Looks like many of us will be using it, so I'll just pull that out there. So our accumulator gets our accumulator at the contents field index. Temp gets temp at its contents field index. Right. And now we can actually do the add. Temp gets the accumulator plus temp. I'm going to push temp. I'm going to need a billion semicolons. Our calling convention may do this, but it never hurts to push and pop something. It just makes it slow. And now we're going to generate code for new int. Notice how often we're making new ints for no reason. It's almost as if some sort of integer unboxing optimization would be an amazing plan. We'll bear that in mind for later. So this is now in the accumulator register. We pop temp, and we want to store. This is a fresh new int, so we're okay. Like right now it holds 0. We're okay changing it because no one else can possibly see it. And it's going to get what's in the temporary register. So this is the accumulator at the contents field index, and it gets what's in temp. And the result is already in the accumulator. Let's hope that works. All right. What do we want to do now? New and dispatch are actually fairly similar. There's some calling convention stuff. But conceptually, we just want to call the thing.new. And it's going to put the result in register A. For dispatch, we've got the receiver object, the function name, and the arguments. And this is a reasonable time to go back to, not the function definition, but a function call. And the slides definitely suggest a way to do this. Do E1 then through EN. But if we actually go all the way back to the cool reference manual, let's see if we can find the rules for dispatch. Notice that we evaluate the arguments first, but then the receiver object. And we are going to need to think about how we deal with the receiver object. So one of the first things we'll do is we're going to iterate over every argument. Maybe we need the number of arguments. Maybe we don't. And we're going to generate code for that argument and then push it. So there's some calling convention stuff, right, which we will eventually have to nail down. Like, I'm running out of time to push that off. But we're going to push that on the stack. And then we're going to generate code for the receiver object and push it on the stack. And then eventually we just call the entry point. But this is actually where dynamic dispatch comes in. We've got the receiver object. We have the receiver object in accumulator. Someone wants to invoke the outint or main method. We have to emit code to look it up in the vtable. This is one of the key differences between a compiler and interpreter. This is a big difference between a compiler and an interpreter. We can't just figure this out now. Instead, we have to emit code for a table lookup. So, step one, load the receiver object, the accumulator, vtable into register temp. Second, load the function pointer index. Let's call this the vtable index into temp2. Step 3, all right, we're going to actually get the method pointer. Right? Step 4, call temp. So where do our vtables live? For us, we put all of our vtables at index 0. Right? You may put them somewhere else if you have type tags or size fields or whatever. So we're going to load that temp gets the accumulator. So this is temp, this is the accumulator, and this is the vtable index. Right. And now we're going to load the immediate value. Temp2 gets this method vtable index. What's that supposed to be? Well, it's actually something we could get when we are laying out virtual function tables. We know the type of this dispatch expression, right? Because, this is like a hint, right? In real life, you have the type of the receiver object. Using the type and the method name, you could have stored, this is hint, store the index associated with this type method name so that you can look it up when emitting code for dispatch. So let's say that we had some sort of vtable method index hash table. Right. For us, there are only two methods of interest, and I'm just going to skip the types. Right? Fix me. I am skipping types. You should not. But when we were generating our code, right, we know that new is always at offset 0, that outint is at offset 1, and that main is at offset 2. So then down here, when I had that big question mark, fix me, that becomes refined in this vtable method index hash table. We look up the function name. All right. So we have loaded the vtable index into temp2, and now we're on step 3. We're going to load temp gets temp bracket temp2, and indeed we don't actually need phrase this, learn the vtable index. Right? And then emit temp gets temp.index. And it turns out we don't actually need to store it at runtime. We know it's 5. We can just emit, or we know it's 1 or 2. We can just emit code that says 1 or 2. And now it's time to call temp. I'm going to call indirect through a register. And then there's some calling convention stuff. And then the last one is internal. And one of the things we can do is IO outint. All right. This is another big difference between, compilers, interpreters, and what you have done previously. We must actually arrange for the integer to be printed, typically via a system call or standard library function. Right. But we have to do this work. I believe cool provides, find it, come on, outint. Cool provides a particular system call, io.outint. Let's just go see. Reads the value in R1 and displays it as an integer to the user. R1 should be a raw integer and not the entire large boxed cool int object. Now that's good to know. I really wish I could copy and paste stuff. Huh. So we'll just we'll have to remember that. So what I want to do is get the raw value of the integer into R1. Right. Well, we made a little promise to ourselves earlier. Let's get rid of that. That the raw value of the integer was called something like contents. Right? But potentially, when we're talking about arguments, we'd said before that outint does not have any arguments. But actually, let's say it does have one. We'll call the argument x. Right? In a programming assignment 4, you gave a specific name to IO outint's argument. What did we actually call it? Let's go find it here. Base classes IO. It is called x. Right. So then, all we have to do is call cgen and generate code for the variable x. This puts it in the accumulator, which is conveniently R1. Making a little note to myself just in case I ever decide to change that by optimization later. Now, we do have to extract the raw contents, and we called that the contents field index. But now, we can call io.outInt. Fix me. This returns a raw integer, not a boxed integer. Something for you to think about later. All right. Now, for debugging purposes, it's often super handy when you're generating code to be able to print out what's going on. So we're just going to have a little expression to string method. This is just debugging. Print that out. If it's plus of E1 and E2, then we will have x to stir E1, x to stir E2. If it's new s, we've got new s. If it is internal s, we've got internal s. If it is variable s, we've got just s. And if it is dispatch of the receiver object and the function name and the args, we will have the receiver object dot function name, and we will not print out the arguments. So when we are generating code, we'll just make a note of what we believe we're generating code for. And indeed, sometimes it's nice to know when you are entering something, and also when you're leaving something. So we'll begin. All right, what are the odds that this actually compiles? Almost nothing. 127. Expression has type string. Oh, you're so right. I've been forgetting that every one of these needs to point to our output string. What I should have done is make a... I should have partially applied it, blah, blah, blah. There are things I could have done. Like making a little helper method to print these things out with tabs. But what can you do? Well, you could make a little helper method to print things out with tabs. Not to put too fine a point on it. Say I'm the only bee in your bonnet. Line 158, printf problems. The contents index field, I know it's 1, but let's use %d just in case it changes. 162, random hash table hackery. 162, random hash table hackery? We have to pass in, whenever we call CodeGen, we have to pass in the symbol table. Similarly down here. 174, function application is partial. We almost certainly don't want that. We have to pass in the symbol table. Pass in the symbol table. 173, the list we're going over is the arguments. 300. This is partial. Oh, we need to make the symbol table. Oh my gosh. Yep, we'll definitely need to do that. 319. We need to make the symbol table, and they're a little different in initializers than they are in methods. All right, and then it tells us not found, and indeed, I'm not surprised. All right, let's we're going to fake this up a bit, right? Where if something isn't in our symbol table, we're going to emit code for it anyway. Try match with anything goes to register not found. All right, so we produced cool assembly. Our vtables are still reasonable. Our constructors, all right, we've got object new, int new, but remember in main new we had those like 222 and 333 values, and the hope is that we can actually generate code for them. Right, so somewhere in here, all right, the B field of main gets a default integer. And then look, we are trying to generate code for 222, which requires us to generate code for new int. And then once we get that, we store a raw 222 in its contents field. And then back in the self object, we put in this R1, which is going to hold 222. All right, that looks pretty good. Similarly, IO out int, somehow we're going to have to generate code for x, like it's probably on the stack, it's one of the arguments. But once we have it, we get its contents field and then call out int. And then for main, A and B, they're not on the stack, they're going to be fields of the self object. So we will want to generate indexed code for them as well. But somehow we find A, somehow we find B, and then here's all of our super complicated addition code. And then down here in start, we're calling new main.main. Here's the new main. And then once we have it, this is emitting code to find the vtable and then find the some method's offset in it. Actually, let's just document that while we're here. This is dispatch, so now this was plus. Where was dispatch? All right. I'm going to load the vtable, and then here it's lives at index blah. So this is the function name. So now when we go to read that again, we're loading the vtable into R2, and we believe that the main method, which we could even make it even clearer that it's a method, lives at index 2 in the vtable. Is that true? 0, 1, 2? 0, 1, 2. Oh my gosh, it is true. That's super convenient. All right, so now we need to A, make these symbol tables, and B, finally figure out the calling convention. And these things are linked. So now we actually have to do the calling convention or the prologue, right? Fix me all of this calling convention stuff. And we're going to, nope, not here. Yes, here. All right. Potentially we push the frame pointer, and then we make the call. And in the call, they move the frame pointer gets the stack pointer, push the return address. We'll also want to get the self object, overwrite the self object, right? Which means that we probably want to save the self object. So the big difference between what's in the slides don't cover object-oriented code generation. All right, so when we're getting ready to call something, right? Somewhere up here around dispatch, before we generate these, right, we push the frame pointer. And I'm just going to make a note of everything that's part of the calling convention. I'm going to push the frame pointer. And then right before the call, we do at some point want to make sure that we're not overriding the self object too badly. The self object stored in R0. So I'll have to think for a minute about exactly where we want to do that. This means, though, that once we start generating code for a method, so we're handling calling convention stuff, was there anything particular to do on the way out? We pop the frame pointer right after the call. So we pop the frame pointer, and this is calling convention stuff. Similarly for new, presumably then, we push the frame pointer and pop the frame pointer. There are no particular arguments to a constructor, and also note that a constructor has no arguments, including no special self-object hidden zeroth argument. All right. Are there other places where we talk about evil calling convention stuff? All right. So calling convention stuff in the constructor. How much of this applies? When we're generating code from the body, one of the first things we do is move frame pointer gets stack pointer. And we also want to push the return address. All right. And then we generate this code. And when we are finally done with all of this, we are going to pop the return address. All right. And they say we want to add stack pointer get stack pointer plus z. We've pushed the return address and we've popped it. So n here is 0. It's 2 for them, but it might be 1 for us. They push the frame pointer and they pop the frame pointer. Yeah, it looks like we don't necessarily need this. Stack pointer gets stack pointer plus 0. Check. Or we can even we can't do that in cool. All right. We may need to adjust this stack pointer more. All right. So then in here, when we're generating code for the body of a method, one of the first things we do is move the frame pointer, get the stack pointer. And push the return address. It may be that for the special start method, we don't need to do this. Right? If the method name is start, then don't do this. But we'll maybe it won't hurt. Can't hurt might help. And then on the way out for calling convention stuff, the return address gets the top, and we add stack pointer gets stack pointer plus z. All right. So the top of the stack is, how do we do top? Stack pointer 0 points to, just double check this with cool assembly. Those are the only times that there's an explicit support. Stack pointer starts at a very high value and grows down. Push takes R1, stores it at the given address. Pop decrement stack pointer, or increments, so stack pointer 1. All right, so this is the calling convention, and indeed, we believe this is obtaining the top of the stack. All right. We want to load immediate into temp2 some number z. I guess we could even put it in temp. And then we're going to add to the stack pointer plus z. And this is part of our calling convention. So this is the stack pointer gets stack pointer plus whatever's in the temp register. All right, so what is z supposed to be? Well, for them, it's, or in these slides, it's n plus 2. All right. And what we often will want to know that in these methods, we'll want to know the number of arguments. Right, so over here in methods, where was it? This is something that we would, methods, totally have obtained from the annotated abstract syntax tree. So this has 1 argument, this has 0 arguments, and this has 0 arguments. So method name, number of arguments, so z, we'll put number of arguments plus 2, but fix me, this is not correct. They're almost certainly not correct. One of the other things we need to do, potentially before we push the return address, the caller has gone to all this trouble to push the arguments like arg1, arg2, arg3, but then the receiver object. Right, so caller has pushed, so we want to set self gets receiver object. So we just had this a bit ago, but just to make sure, how do we actually read the top of the stack? Increment stack pointer by 1 and then loads the value from it. Right, so this is calling convention get receiver object, and this would be self, and then we can push the return address on top of that. And now, well, unclear, this may be correct. We've got arg1, arg2, argn, receiver object, return address. So n plus 2 may actually work for us. All right. But for many of these, like frame pointer gets stack pointer, for us, if method name is not start, then do these things. If it's not this special start method, because there's no caller to start, it comes out of nowhere. And then, how does this actually end it? If it is start, call R2. If the method name is start, then begin, and else begin, and all right. So we have our first stab at a calling convention. Now, are we going to get the calling convention right the first time? Almost certainly not. This is a huge amount of debugging. But now the last remaining sort of code thing to do is to start handling the symbol table. Right? And we had the number of arguments, right, in our methods before. Right. But actually, let's name them, because that will help with our symbol table. All right. So these are the args. So as we're going to create this symbol table, right, when we call, point dot, set x of ux, which is an integer, there are a few variables in scope. First, all of points fields, x, y, color. Second, and overriding, all of set x's formals. Right. These live at offsets from the receiver object. These live at offsets from the frame pointer. Right. So to make this symbol table, we're just going to go over or iterate over all of the fields and all of the formals. Step 1, fields in scope, formals in scope. Right? And for now, right, I'm just going to hack this. We'd actually use type information, but somewhere up here we have, in our class map, right, where was it? All of the fields, right, associated with various classes. So fix me, this is a hack. All right, and we've got the field name, the field type, and the whatever. Right. In reality, right, do not use every class, but we have so few classes that this will potentially work. All right. We've got this. This is really more like a list of fields. We're going to go over the field name, field type, and initializer, and say that we believe, right, we're going to add to the symbol table that this field name will live at an offset from self, right, at position index, and then we will increment index. So this was step 1, all of the fields in scope. And then step 2, all of the formals in scope. So this time we're going to iterate over all of the arguments. And this is where we need that magic formula. This was discussed in the slides briefly, but to look up, right, if the frame pointer is currently here, it's something like the frame pointer plus z, where z is n plus 1 minus I. Right? So n is the number of arguments, right? this is a particular index, this is I, potentially starts at 1. All right. But these are an offset from the frame pointer. And we said that it was something like n plus 1 minus I. But it turns out that from our perspective, there's one more argument, because after we pushed 1 and 2, we pushed the self object. All right. So there may be another plus 1 in here. And now we have our symbol table that's more accurately mapping where we would find any variable that we're looking for, right, when we're making this call, or when we're generating this code. Now, debugging that's going to be tricky. So indeed, right, where with register R. We'll just have a little printout for where everything is. All right. V is at R, or V is at RI. Right, this is just debugging information so that we can double check our symbol table and make sure it's working correctly. Can we compile this? 382, that's not handy. 328 might be unmatched. All right, this is more handy. Yeah, they're right. We've got this begin and end. We had our symbol table. We did this new iter. Oh, that was bad. All right. So list iter. Yep, we forgot that. List of fields. 347, iterating over the class map. Yeah. Trying to reverse engineer the order of arguments to hash table iter. All right, that looks good. They like that one. They're right that when we reference I, and then we have to increment I. 359. I meant arg name. 376. Format string error. They're right. Unused variable num args. All right, fine. Well, let's see how close we are. So, potentially, we start way down here at the bottom, pushing the return address. We're generating code for new main. We push the frame pointer. We push the frame pointer again. Sadly, this is super common. Super common with machine-generated code. But we are eventually calling main.new. Good. We pop the frame pointer. All right, that's all fine. We push R1, which is holding this new main object, but we also call it, and then finally when we get back, we do all of this junk that's unnecessary before calling exit. All right. So what actually happens inside main.main? Well, when we're inside main.main, we're generating code for self.outInt, and we believe that A lives here, that's good, B lives here, that's good, and contents, if we had it, would live there. There is one other thing, though. when we are making this symbol table, right, there's one other thing we always have access to. Self lives in register self. All right. So now let's go back to main.main. When we're generating this code, we think A lives at register 0, offset 1, B lives at register 0, offset 2, and self is register 0. So what is main.main actually trying to do? Call self.outInt of A plus B. All right, so we're trying to call self.outInt. So one of the first things we do is push the frame pointer, and now we're trying to generate code for A plus B. So one of the first things we'll do is load A, which we should be getting from register 0.1. Oh, and we do. So then we get its value, and we push it immediately on the stack. And then we get register 0.2, and it's now in the accumulator. We pop A into register 2. We get both of their contents. We add the contents. We save this. We make a new integer. Right, great. Call int.new. We pop the saved R2 from up here, and we store in the contents field. Looking good so far. And now we are about to call, we're trying to generate code for self, which we just get from R0. Good. And now we are trying to call outInt. So we've moved self into R1. And we're loading the vtable. Great. And outInt lives at index 1. Does it? Yes. Good. And then we eventually call that, and then we return. So when we did this, we pushed A plus B, and then we pushed the self object. So let's go take a look at outInt, because here there's a special X field, which is at frame pointer plus 2. Well, we hope. We'll see how this goes. All right, so at this point, it's actually not impossible that we could try to run this cool assembly, although it would almost certainly crash. Line 3, syntax error. Did I? Oh, gosh. All right, line 76, error near. All right. This is quite correct. We can't store this 222 here immediately. We'd have to put it in temp and then store it. Right, so we're not generating correct cool code. So when we're doing these integers, this step wasn't quite right. Instead, we have to load into, say, temp, load the immediate value, LD. This is temp and I, and then this becomes temp. As this is a load store architecture. OCaml, cgen, cool, out. All right, and then this section of the show, debugging, is actually where you spend the majority of your time when you're trying to deal with a code generator that's not quite right. We've been talking for quite some time, so let's see about breaking up the video now. That was construction, and then we'll do debugging second.